Hi everyone. So today's topic is conditional probability. So let's begin with it. Okay. So you receive partial information about the outcome and this shrinks your sample space. Conditional probability is just renormalizing probability within the reduced universe. So probability of A given B means that given that B has already occurred, what's the probability of A? Okay, so B becomes the new sample space. Everything outside B is just now impossible to occur for A. Now, uh, formal definition, how you will put it in formula, here it is written. So, probability of A intersection B upon probability of B can be said equal to probability of A given B. Okay, so here that uh, probability of A intersection means that probability both occur simultaneously. Probability of B means that normalizing constant, it's just a normalizing constant. So it rescales, so the new spaces comes to 1. Now, uh, we can rearrange it and get a new formula also like, just a second. Yes, we can just put the denominator here into multiply and we can get a new formula. And this is used and that formula is used constantly whenever you need a joint probability. And there is one more thing, chain rule, like generalization to n events. I guess I have not mentioned this in PPT, but like probability of A1 intersection A2 intersection till intersection of AN is equals to probability of A1 into probability of A2 given A1 has occurred into probability of A3 given A1 comma A2 has occurred, and it goes on. Now, there's a PPT problem, I guess, so it's not loading. Hmm. Okay. Now the next thing is unconditional versus conditional framework. It's just a unconditional means a view from nowhere, and conditional means a view after observing an event has occurred. So in this, the sample space will be the original universe. But in this, probability of A given B, the B will be the new sample space for A to occur, and the formulas are written here. Now the next thing is, okay, here is the rearranging slide. Uh, See, I said you know that if we make it here to multiply, we get this formula, and this is now because of symmetry, this is also equals. Okay, okay, we got the formula here. Next thing is that proving the intuition, a roll of a dice. Okay, this is a simple question of a die when it is rolled, and given that sum is greater than 10, so what's the probability of sum equals to 12? So how you will find it? First define the events, then find the intersection, and then apply the formula, and you'll get the answer. Now, once you know the sum is greater than or equal to 10, you are only looking at 6 equally likely outcomes, and exactly one of them is 6 comma 6. So, 1 by 6 makes immediate sense from the shrunken sample space view. Okay. So, comparing it to unconditional probability, probability of sum equals to 12 will be 1 by 36, and with the information sum greater than equal to 10, it jumps to 1 by 6. So information change the probability as it should also. Now, next thing is the chain rule of n events. Okay, this formula I told you just 1 minute ago. That probability of A1 intersection A2 intersection till AN is equals to probability of A1 into probability of A2 given that A1 has occurred and so on. So now let's take an example of deck of 52 cards and draw 3 without replacement. Now probability of that all 3 cards are aces will be how much? First of all, there are 4 ace cards. Okay, we know that. So first situation is that 4 by 52. 4 ace cards by total sample space 52. Now the next thing is that now one ace card is already being removed, so 3 are left, and one card is removed, so 51 cards are left here. So this will be the another probability, and then next step will be like this, and after multiplying you will get the answer. Moving on forward. Okay, So flaws in interpretation means where you can make mistake. That first thing, there is a persecutor's fallacy, which says that the probability of A given B has occurred is not at all equals to probability of B given A has occurred. So remember it in mind. And the second thing is like that probability of B is equals to zero makes probability of A given B undefined. Okay, remember it. Probability of B given 0 makes probability of A given B undefined. You cannot condition as on a zero probability event in classical sense. Okay, so this breaks on continuous distribution and requires more careful treatment. And this is like a major theory which we will cover in topic 60 something. So, moving on forward, conditioning on B changes P for everything, not just A. Once you condition on B, the entire probability space is renormalized. Okay, so probability of C given B is not equal to probability of C in general for any event C. Remember it. Now, given that given is not equals to caused by, remember it means that probability of A given B measures co-occurrence structure, not causality. Okay, so it means let's take an example. Probability of lung cancer given yellow fingers is high, but yellow fingers don't cause cancer, both are caused by smoking. So casual inference is a separate framework entirely. Remember it. Now, improper next thing like where we can make mistake is improper in conditioning on the event you are computing. If you condition on an event that's defined using A itself, you cannot get circular or true statements. So always check whether B is logically prior to A in your setup or not. Now, moving on forward, why we are studying this, what is the ML connection? So, naive Bayes classifies it entirely built on conditional probability. And the like simple formula is written also that probability of feature given that class has already occurred. Okay. Next thing, like every probabilistic graphical model encodes conditional independent structure. Then the chain rule of probability is equal to the chain rule used to factorize joint distribution in generative models. And attention mechanism in transformers implicitly compute something like something similar to conditional distribution over tokens. So that's why it's important. So I tried to explain this topic from my side, and if you find any kind of mistakes, you can just say me. Thank you. Bye bye.